And welcome, dear ladies and gentlemen, to my talk about the very high cycle fatigue of wrought magnesium alloy az61. My co-author, Professor Herwig Meyer, has already been presented, but I also like to take the opportunity to present my second co-author, Anton Stich from Audi AG in Ingolstadt, Germany. So let me begin with only some short comments on the material. As already mentioned in the title, the investigated material was a wrought magnesium alloy az61 of high purity. The chemical composition given in weight percentage is 6.3 aluminum, 1.0 zinc, 0.2 manganese and balanced magnesium. Remarkable is the relatively fine grain with a mean grain size of approximately 5 micrometer and a relatively high ultimate tensile strength of 302 megapascal. In order to describe very high cycle fatigue properties, lifetime as well as fatigue crack growth measurements were performed, and the respective specimen shapes that were used you can see here. All tests were performed using ultrasonic fatigue testing equipment developed at Boku with a testing frequency of approximately 20 kilohertz under fully reversed loading conditions. Testing environments were ambient air with an additional high vacuum of approximately 10 to the minus 5 millibar for fatigue crack growth measurements. Sample preparation for fatigue crack growth rate measurements included a mirror-like finish and the introduction of a single edge notch of approximately 1 millimeter by electrical discharge machining in order to avoid any residual stresses. Fatigue crack growth was observed optically on the specimen surface, as you can see here. So let me now present you the results of the lifetime measurements. As you can see, we still observe failure in the gigacycle regime. This means the material shows no fatigue limit. We have a single slope curve with no transition in failure mode. Cracks initiated mainly from the surface, with some rare exceptions where the crack initiated from the subsurface. And no inclusions or other imperfections were found at the crack initiation sites. So because of that, we assumed that the cracks might be initiated by slip bands. And we took a closer look on the specimen surface. Please note this is the specimen surface, this is the fracture surface. And we indeed find some slip bands with even some micro cracks emanating from the slip bands. But still, we were not that sure if these slip bands were the result or the cause of the failure. And considering slip in magnesium alloys, one has to take into account that slip systems are highly restricted due to the hexagonal post-packed crystal structure. And even more due to very high critical residual shear stress, resolved shear stresses, there's only one possible slip system left at room temperature. And it has been often shown by many authors that these conventional extruded magnesium alloys like the az61 are given a pronounced texture during the process, which results in that the only possible slip system, the basal slip system, comes to lie parallel to the extrusion direction, which in our case is also parallel to the loading direction, which makes this slip system very unlikely to be activated. So, but slip is not the only mechanism of cyclic deformation. There's also twinning, and indeed it has been also often shown that twinning plays an important role in magnesium alloys. We were also curious, and indeed we could observe these twin bands on the surface of a specimen cycled at the fatigue limit. And now this twinning, due to the reorientation of the crystal structure, can have a twofold effect. On the one hand, it can open new slip systems. On the other hand, it also can act as a barrier, causing dislocation pileup and subsequent local stress concentrations. So, and if you take a closer look on one of these twin bands, you can see these micro cracks emanating from the twin band, and also this debris indicating slip. So, at the moment we cannot answer this question satisfyingly. We have found indications for slip, we have found indications for twinning, so at the moment we just might assume that the crack might be initiated by twin assistance. But we'd like to conduct further investigations on the subject, and well, then I come to the results of the fatigue crack growth measurements. Crack propagation is plotted here with solid symbols for crack propagation in ambient air. Open symbols are crack propagation in vacuum. Due to very high testing frequency, ultrasonic fatigue testing is restricted to the near threshold regime. And as you can see, the threshold stress intensity in ambient air is significantly reduced due to this plateau-like regime of almost constant crack growth in the range of 10 to the minus 9 meter per cycle. Also remarkable are these very low crack growth rates that can be observed in vacuum, which are below 1 Burgers vector per cycle. So, since we find a very strong indication for stress corrosion cracking in the crack growth curve, we also expect to find some or more evidence for stress corrosion cracking on the fracture surface. And we performed some fractographic investigations, and here the fracture surface in the regime of very high fatigue crack growth rates where environmental influences are suppressed due to very high testing frequency. We find indeed that both fracture surfaces seem to be similar, displaying a rather smooth and featureless fracture surface. But when we go down in the range of crack growth rates where there is a clear environmental influence, we find indeed a pronounced roughening of the fracture morphology obtained in ambient air, featuring these cleavage facets indicating that some sort of embrittlement has taken place to the material. Whereas in vacuum, the fracture surface tends to smoothen, featuring areas of fine granular appearance and numerous deformation trends. And if we take now a closer look on the fracture surface obtained in that regime, we find more evidence for stress corrosion cracking. Already mentioned these cleavage facets, but also corrosion products and secondary cracking. And when we go further down into the threshold regime, we find that the fracture morphology in ambient air tends to smoothen again due to the increasing size of these cleavage facets. So let me now conclude my talk and also give an outlook on the future plan. The very high cycle fatigue properties of wrought magnesium alloy az61 were investigated. The material shows no fatigue limit. The ratio of fatigue strength at 10 to the 9 loading cycles to ultimate tensile strength is 0.32, which is comparable to aluminum alloys. Crack initiation occurs mainly from the surface, probably from slip bands. And we could show that environmental influences are effective even at ultrasonic frequencies. We found a distinct or pronounced reduction in the threshold stress intensity factor in ambient air compared to vacuum of about 42%. And fractographic investigations reveal a transition in fracture mode from ductile to quasi-cleavage, suggesting most likely hydrogen embrittlement to be the acting process. So, the future plan, we'd like to conduct further fatigue growth rate measurements in dry air in order to answer the question whether it is hydrogen embrittlement or something else. And we also like to further investigate the evolution of slip and or twin bands and their effect on the crack initiation. So, thank you for your attention.